Think about how we understand physical capacity. In a parking lot, a stadium, or a standard hotel, the logic is rigid. You have a set number of spaces. When every one of those spaces holds an object, the structure is full. You are out of room, and it is impossible to accept anything more. Mathematician David Hilbert wanted to test the limits of this exact intuition. He constructed a theoretical proxy designed to follow mathematical laws rather than the restrictions of physical reality. Picture a hotel stretching endlessly, door after door, numbered 1, 2, 3, continuing forever. Every single room is currently occupied. The register shows infinite guests, perfectly matched to infinite rooms, 0 vacancies. Then, the lobby doors open and a single new guest walks in looking for a room. In a physical building, the manager would turn them away because physical volume dictates capacity. But in Hilbert's construct, we have to separate physical space from the way we map numbers. The manager doesn't hesitate. He prepares to accept the new arrival. The manager issues a simple instruction to every current guest. Everyone in room N moves to room N+1. The person in room 1 moves to 2. The person in 2 moves to 3. And the entire sequence slides forward by 1 position. Because the line never ends, nobody is pushed out of the hotel. But watch the front of the sequence. Room 1 is now completely empty. The manager directs the new arrival to the first room, and the registration is complete. At the scale of infinity, full does not mean out of space. It simply means every item is currently mapped. As long as you can change that mapping, you can create a vacancy without adding any physical volume. Handling one guest was a simple fix, but now a giant bus pulls up to the lobby, and this bus is carrying an infinitely large number of passengers. Shifting everyone down by 1 won't help here, as that only creates a simple vacancy. Instead, the manager doubles every guest's room number. The guest in room 1 moves to 2. The guest in 2 moves to 4. 3 moves to 6. The math instantly creates an alternating pattern. Every existing guest is now in an even-numbered room, leaving an endless sequence of gaps at every odd number, 1, 3, 5, 7, and so on. The infinitely many passengers step off the bus and fill those odd-numbered rooms. The hotel absorbed a geometric expansion without adding a single room, proving that infinite sets can be compressed to make space for themselves. The ultimate stress test arrives next, an infinite convoy of buses, where every single bus holds an infinite number of passengers. This is a mapping problem. Every passenger now requires 2 data points, their bus number and their seat number. This creates a 2-dimensional grid of coordinates hovering over our single 1-dimensional line of rooms. You cannot count row by row because the first row never ends. Instead, you trace diagonally. By zigzagging through the coordinates 1, 1, then 1, 2, then 2, 1, you ensure every single combination is eventually visited. Nothing is skipped, and nothing overlaps. The entire grid collapses into a single sequence that fits flawlessly into the hotel. This is known as countable infinity. It establishes that as long as an endless set can be ordered into a single list, its apparent dimensions do not change its mathematical size. The massive grid is the exact same size as the list of rooms. We have stretched and folded infinity, and the logic has held. To finally find the breaking point, we have to look between the whole numbers and introduce the real numbers, every possible decimal between 0 and 1. George Cantor investigated the continuity of these real numbers to see if they could be mapped like the guests on the buses. We map rooms to decimals, assuming we'll eventually house them all. But Cantor proved this incomplete. By altering the first digit of the first number, the second of the second, and so on, he constructed a new decimal mathematically guaranteed to be unlisted. No matter how many rooms you provide, you will always be able to construct another number that isn't inside. The decimal continuum is mathematically unlistable. Between any 2 numbers are always endless more, making this a larger, more dense form of infinity. We are left with 2 different states of existence, a countable infinity that can be rearranged and mapped, and a continuum so dense it refuses to be contained in any sequence. Hilbert's thought experiment reveals that the infinite isn't a single destination, but a hierarchy of distinct levels. It shows us that once we step beyond the finite, the rules of capacity change, and full is only the beginning of the story.